All right, we're recording. This is the official start of class. We have 2 for. It's never been done. I don't know for sure. Tyler Shepard? Yes. Okay. So we'll be at the end, I hope. Wait, what happened? I live. Peter Schoen. Okay. So now we're down to Mark, Brendan, and Ibrahim are not here. And I'm going to have to talk to Ibrahim. Mark? Yep. Technology makes our life more efficient. They decided to take my BB Learn shell and put a limit of 500 megabytes on it. And I don't have any videos posted to it. I honestly don't. I just have a lot of PDFs. I got a lot of review materials in there. And so I had to, I'll stand back. So I had to complain to ETS today. Okay, so we've gone through first and second order circuits using transient analysis. What you did in EE280, you started out with DC circuit analysis, and then you did AC circuit analysis, but it was always AC at a single frequency. Now we're going to look at the case when my AC sinusoidal signals may be varying in frequency, or they may not even be sinusoids. So we need a whole nother kind of suite of techniques that we'll throw together when we get to the next section, the 05 section. This is 03. We'll put it all together in circuit analysis, but there's some basic math you need to learn first. And unfortunately, I'm going to teach it to you. I wanted to teach this class because of the electronics. Homework 3 was due today. We'll work on lab 2 again this week. There's no lab due this week because lab 2 continues. Lab 2 is due, when is lab 2 due? Probably, yeah, right between the exam review. Your exam, we're gonna have an exam review day. It's coming up fairly quick, end of the month. In Frankie 436 for last Wednesday's A3PE. On Wednesday, the last half of the class will take exam 1. It will be a different exam, but same level of difficulty. I know how to do that. And if you absolutely cannot take the exam in person, you need to email me about a week in advance and I'll set up a time for you. Probably on Tuesday, February 3rd, knowing my MO. But you need to email me in advance so I know that I'm going to be able to do that. And we can agree on a time beforehand. If you come to me the Thursday or Wednesday after the exam, I'm sorry, you know, it's just too late. So let me know if you want to take the exam remotely. It's easier to take in person. You don't have the technology stuff to worry about. It's a format you're used to, you're comfortable with. Everybody, and then I get the papers from the people who take it online, and they're hard to grade because they're all messy and they're out of order. And yeah. Okay. So Laplace transforms, today we're going to do part 1, and we'll finish this up next class, which is Wednesday. So we'll look at a few examples of circuit analysis and some definitions. The magic tables and transform properties, then this is like the first couple of times I taught this class, I had to literally walk around with this looking things up. You can take these and put these on your note sheet for the exam. And I highly recommend you do that. I know one person who did it without it, but he was really smart. And then the next part is inverse Laplace transforms, which involves this horrible thing called partial fraction expansion. I'll show you my shortcut for that. If you have a TI Inspire calculator, I know that one in particular will do a partial fraction expansion for you. Be careful and double check it. If you just write the answer down on your exam, it's all or nothing, no partial credit. If you show steps and I figure out where you made the mistake, I can give you partial credit. But if you just write it down from your calculator, make sure you do it twice, that you get the same answer. That's what I would have done. Now here is an example of a horrible circuit. Let's look at this. What is our goal? Our goal is to find V out of t if V out of 0 plus is 5 volts. So I initially have some charge stored on that capacitor. I've got these sources in here. Sorry about this. One is a delta function. So it's infinity at time, it's twice infinity at time t equals 0. It's 0 every place else. I'm not too sure how to analyze that, or you're not too sure how to analyze that yet. I've got another function here that's an exponential. And it's an exponential that cuts on at time t equals 0. That's what that U of t does. We can't use DC analysis because it's not a DC circuit. We can't use AC analysis because it's not a single frequency sinusoid. We may be able to do transient analysis, but I'd have to have a 0 minus circuit here, a 0 and a 0 plus, and I don't know what's going on in between there with the delta functions. That's weird. And then on top of this, I have, this is switching, but when it switches on, it looks like this. It's 0, and then it gets to time t equals 0, and then it decays away. I would have to do a switching function at every infinitesimal piece of time to get that one. So I don't want to do any of these, and that's all you know how to do so far. So let's just start writing the node voltage equations, which is always my last resort when I can't figure out any way else to do it, but it works for every circuit. So for node voltage, I assign a ground node. I'm going to put it here. And once I assign that ground node here, that tells me that I know VA. VA is just going to be 10 e to the minus t u of t. Now I have to assign current directions. Remember, it doesn't matter which way I do it, just as long as I do it. So it's the node voltage method is I'm writing a KCL equation at node B. Sum of the currents going in equals the sum of the currents going out. So the current from this 10 ohm source is 10 ohm resistor is just going to be VA minus VB over 10. Well, we have an expression for VA. So that's 10 e to the minus t u of t minus VB all over 10 is that current. The other 10 ohm resistor, the one that's going down, goes between VB and ground. So that's plus, and that's going out. So it goes on the other side. The other one that's going in to the node, let's do that one first, is 2 delta of t. And that will equal the sum of the currents going out, which is that second 10 ohm resistor. So that's VB minus 0 over 10. And, oh yeah, there's a capacitor in there. And the current through a capacitor is I equals C dV dt. So what I've got here, its current is C dV dt. Okay. That's the equation that we have to learn how to solve. No. And I didn't even write that. There's the equation. I've got derivatives in there. I've got exponential functions in there. I've got U of t's. I've got deltas in there. I don't know. I do not even know how to solve that equation. The way we actually solve this is we're going to use Laplace transforms. It's kind of like what we did in the AC part of EE280 where you put the circuits in the frequency domain. Now we're going to put them in the S domain, which is an awful lot like the frequency domain. We're not going to get to all these pieces today, but I start with the circuit in the time domain right here. I transform it into the Laplace domain. So this gets to be this 10 e to the t, e to the minus t u of t, becomes 10 over s plus 1. Resistors stay the same. They're always reliable. My capacitor, you learned that the capacitive impedance was 1 over j omega c. I'm going to change the j omega variable to s. S is really sigma plus j omega, but it's close enough for this. And a lot of times I just drop the sigma. So this is like 1 over SC. So I'm going to make this 1 over S 0.1, which is 10 over S. And I'm going to leave the S in there as a variable because the frequency can change. This little bugger here represents the initial energy stored on the capacitor, and yes, it does really exist. When I Laplace transform 2 delta of t, it comes out magically to be 2. So this is a circuit I can solve. It's going to involve some messy algebra. I'm just going to show you the example. By the end of this, you should be able to solve the circuit, but not today. This is the equation in the time domain. We don't want to solve that. This is the equation in the S domain. Once I transform that circuit into the S domain and write the node voltage equation, I've got messy algebra. I'd have to multiply the whole thing by S to get this out of the denominator. I could multiply this fraction by S plus 1 over S plus 1 to clean that up and come up with V out as a function of S. Okay. This step is doing a partial fraction expansion on that. And then the final step, I take the inverse Laplace transform and I have a solution. It'll take us an entire week to get to actually being able to do that. So there's a lot of steps in there, but that's the big picture. I want to put the circuit in the frequency domain, S domain, frequency domain. I'm going to turn this really messy equation right here into something that is just algebraic, so it's possible to solve. And then I'm going to solve it and then take the inverse Laplace transform, and I'm done. I don't know how to solve the first equation. And I think most mathematicians who saw that would probably say just put it in the S domain even. So this is the guy who came up with this idea, Laplace, Pierre Simon Laplace, because it's written down there. The definition of a Laplace transform of a function of time is going to give us a function of S, and S is like frequency, and we'll talk about that a lot. And the next unit after this is Bode plots, which you'll hate me for, but that's okay. They're useful. I should just rewrite that. And the definition of this f of s, it's the integral from 0 minus to infinity of f of t e to the minus st dt. And it transforms those integral differential messy equations to algebraic equations that you can solve. And this is what lab 3 will be. And I apologize for lab 3 too. I'll be there. In addition, one thing I want to point out on this, the limits of integration are from 0 to infinity. So anything that happens before your arbitrarily defined t equals 0 is completely wiped out. You lose all information about things that happen. How did that happen? I wasn't even writing. You lose all information about what happened at t less than 0 before you do that. I will come back to that, and I will be back in about 30 seconds. I wasn't even writing on the screen.